When we talk about electromagnetic waves, it's important to consider how fast they are. In 1680 or 38, what Galileo attempted to do is to try to figure out how fast light is. And so, him and a assistant went to opposite hilltops, and Galileo told his assistant, as soon as you see my lamp, open yours, and then I can, maybe estimate, how quick or how long it takes for me to see it. And then obviously, they found that it was way, way, way too fast. And he determined either the speed of light is infinitely fast, or it's so fast that with human error, we're not going to be able to figure out how fast it is. And so Galileo had a lot of forward thinking, and this is one example of his, thinking there with that progress. So it's kind of neat to think about, the speed of light being as fast as it is. Um, you know, it's still, you know, it's very, very fast. Um, all right, so now we're ready to talk about electromagnetic waves. And electromagnetic waves are right within the word itself is what they are. They're made of electric fields, and they're made up of magnetic fields intertwined. And the mystery of light, continued for a long, long, long time. Scientists, debated what a light was about. Newton thought it was a particle, and then Huygens came along and said, no, it has wave characteristics. And so, it's been debated for a long, long, long time. We have a much better idea or understanding of light, and its connection to, order in the universe. So the kind of waves that we've looked at are mechanical waves, and they've all had to have a medium to go from one place to the other. Um, and from the early on, Greeks knew that sound, needed a medium for it to go through. If we put a sound source in a vacuum, there's not going to be any sound, right? So if we take all the air out and we place a radio inside, you're not going to get any sound. Um, from the middle to the end of the 17th century, Hooke and Huygens proposed that just as with sound, light needed a medium. And so this transfer, they were thinking, yeah, we know sound waves need a medium, light must need a medium. So they created this idea that there was this medium called ether that light went through. And it wasn't until 1887 with Michelson and Morley that they found that light was very different than sound, and doesn't need a medium. And so it's interesting how analogies can actually sometimes slow the progress of science. Sometimes you assume things, and maybe your assumption is incorrect, and so it's important to challenge your assumptions, as you go along. What I encourage you to do is go to Google search PhET and then EM wave simulation. Or you could just, take this and take the URL and place that in there. And this is a great simulation. I like to show this to show some of the, parts of what's going on, what's creating a wave, as it propagates out from an antenna. So what happens is the way that a electromagnetic wave is formed, at least a radio wave, is that you take current and you send it through a wire like this. The current, when you close the switch, the current's going like this. And when you do, let's say this is the negative terminal, and let's say this is the positive terminal, you're going to have a electric field being created, and you're going to have these electric field lines that are going to go from the top down to the bottom. Now, it turns out, too, that at the very same time, using a right-hand rule, if you take your pencil and you grab it and you put your thumb towards the top of your screen, on the right-hand side, you're going to have a field that's going in, and then on the left-hand side, you're going to have a field that's going out. And so the magnetic field is going to be created perpendicular to the electric field. And that's actually what happens. The current's going up, and then a split second later, you can have make the current go down the other direction, and then flip it back and forth, and you're creating these electric fields and magnetic fields that are intertwined. And so in this case, this is what like the first picture we saw here. This is just showing this is alternating. The current's going up. The electric field in red is going like this, and then the blue represents the magnetic field B. And then, a split second later, we can reverse the current and have it go down. Now the positive side is down here. The field is coming up and around like this, the red. And then in blue, we see that the magnetic field is coming out. And so it flipped, right? The magnetic field and the electric field flipped. And you can send that back and forth, back and forth, back and forth at a very specific frequency. And when you do that, you create the electromagnetic waves. And, they can propagate out from there. Now, the antenna being here, right, they have the waves going out. And what happens is as it spreads out, it doesn't take very long for it to get to where they're basically parallel to each other. These wave fronts are parallel to each other. And so by the time it hits your radio antenna or your house antenna, these wave fronts hit one right after the other as a plane wave. And we see that there. This is a visualization. I'm not going to be able to play it on the screen here, but you can see this. This is an intertwined electric field and a magnetic field. And if you notice, with the electric field and magnetic field, they come up to a maximum, and then they go to zero, and then they go maximum the other way, and then to zero, and so on. But they're perpendicular to each other. They're transverse. So they're transverse electric field, transverse magnetic field. That's going through here. This picture may be a little bit easier to see, having the X, Y, and Z axis here. The electric field is going up and down along the Y axis across the X here, and then the Z axis is the magnetic field in and out of the page. And they're perpendicular to each other, and they are transverse waves, making up electromagnetic waves.